let's talk about the motions of the terrestrial planets. But before we do that, we've got a question. What is Doppler shift? A, the change in wavelength of light due to relative motion of the source and the observer, or B, the apparent shift of objects as the observer changes location. Okay, so this is our third clicker question. Go ahead and think about it, and we'll discuss in just a second. The answer is A, the change of wavelength because of relative motion. Hey, do you remember what B is? B is parallax. Okay, so the apparent shift of objects as the observer changes location, that is parallax. Okay, but the change of wavelength due to relative motion, that is Doppler shift. So it is really hard to see Mercury, or at least to see it clearly. So because it is closest to the sun, it's always going to be close to the sun. Now the very best time to actually see anything is when the sun is down, and we want the object to be up high in the sky, close to the meridian. If it's close to the meridian, we're looking through the least amount of atmosphere, and if you remember back, the atmosphere does terrible things to light. So we want to look through as little atmosphere as possible. But with Mercury, it's always going to be close to the sun. So if Mercury is near the meridian, the sun is up in the sky and you can't see Mercury anyway. So we have to wait until after sunset or before sunrise. But then we have to look through lots and lots and lots of the atmosphere, which is going to significantly distort and mess up the light. Okay, so what this means is it's hard to see a good image of Mercury's surface. Okay, so in this picture, this is what we can kind of see of Mercury's surface. And you can't really get much detail. Without actually seeing detail, without seeing craters or other features, then we couldn't figure out how fast Mercury was actually rotating. Okay, so at first, when people were considering Mercury, realizing how close it was to the sun, they figured that it probably had synchronous rotation. Okay, maybe Mercury actually had synchronous rotation. Okay, well, if you remember, synchronous rotation is where the object always keeps one side facing towards what it is orbiting. So this is what's happening with our moon, why we only see one side of the moon. Okay, so its rotation rate and its orbit take the same amount of time, so one side's always facing. Okay, in this case, one side of Mercury would always be facing the sun. Okay, well, we didn't figure out its actual rotation until after the invention of radar. Okay, so what we did is we send out a pulse of radio waves. Okay, now all of these are going to have the same wavelength to begin with. When these radio waves reflect off of Mercury, the side that's moving away from us, the returning light, will be red shifted. Okay, the side that's coming towards us, the reflected light from that side will be blue shifted. So we get a red shift and a blue shift, which are going to tell us the speed that Mercury is rotating. How fast are these two sides moving? Well, if we know how fast they're moving, we can then figure out the total rotation rate. Doing this, we actually were surprised. Mercury does not, in fact, have synchronous rotation. Instead, it spins 1.5 times every time it goes around the sun. If it was synchronous, it would be one rotation for one orbit, okay? But it's actually 1.5 rotations for one orbit. Okay? So it's not quite synchronous, but there is a relationship. Okay? So for every 2 orbits around the sun, Mercury is actually rotated 3 times. Now, this is likely a consequence of Mercury's eccentric orbit. Remember, it swings in close to the sun and then goes farther out. When it's close to the sun, it has one particular axis that it wants to have pointing towards the sun, or at least that gravity wants to have pointing towards the sun. Okay, so we have that particular alignment. Then, as it swings farther away, gravity decreases, allowing Mercury to spin some until it comes back in and wants that axis pointed again. But now that axis will have flipped by 180 degrees. So we get 1.5 rotations for every orbit. We can actually see Venus fairly well because we can see it after sunset. However, when we do, we actually see the cloud tops, and the clouds don't necessarily move the same way as the surface of the planet. So again, we had to turn to radar to figure out how it is that Venus is actually rotating. When we did, we found, again, a surprise. Venus has a retrograde rotation. Do you remember retrograde? Hey, this means that it is rotating backwards from the way it should be. According to conservation of angular momentum, planets should be rotating and orbiting around the sun in the same direction. Okay, so if you're looking down on top of the solar system, the planets are orbiting counterclockwise. This means they should also be rotating counterclockwise. Venus is not. It is rotating clockwise. What this means is that on Venus, the sun rises in the west and sets in the east. Okay, so this is really weird. Well, if you remember back, our go-to explanation for anything weird with the planets is a giant impact. How did the explanation for anything weird like this is giant impact. Okay, so one possibility for why Venus has a retrograde rotation is that it got hit really hard. Okay, when it first formed, it was rotating in the direction we expect. Then something came in at the right angle and knocked it, so now it's rotating backwards. This is one possibility. Another possibility, as we've studied Venus, we've seen that the winds go in that same clockwise direction, retrograde direction. So some have suggested that maybe over the course of 4.5 billion years, the friction between the atmosphere and the planet has caused it to slow down and then start rotating the other direction. Okay, which of these is actually correct? We don't know. So when this happens, where we have two competing ideas that seem they could both work, hey, I like to go with what I call the coolness rule. Hey, which of these would look better, would actually seem better to look at? Hey, so in this case, I'm going to argue for the giant impact. A giant impact smashing a planet, causing it to rotate backwards, is going to look a lot better than wind blowing over the surface for billions of years. Hey, when we look at Mars, Mars's rotation and tilt are actually very similar to the Earth. Okay, so the Earth's axial tilt is about 23.5 degrees. Mars is around 25 degrees. Okay, and a Martian day is only 38 minutes longer than an Earth day. So it actually has a lot of similar motions to the Earth. Now its year is a lot longer because it's farther away from the sun. Okay, but other than that, it's got a lot of similar motions to the Earth. Okay, because it has a similar tilt, that 25.5 degrees, it actually has seasons similar to the Earth. Okay, so there is a spring, summer, fall, and winter on Mars in the northern and southern hemispheres, just like we see on the Earth.